until this point, we have been discussing the structure and isomerism of coordination compounds and complex ions. We talked about both structural isomers and stereoisomers. So now that we've talked about the structure and isomerism of coordination compounds, we want to start thinking about the properties of some of these coordination compounds. So many coordination complexes or complex ions are colored. It's one of my favorite things about coordination complexes. So these three examples, hexa aqua chromium 3+, hexa aqua iron 3+, and hexa aqua cobalt 2+, these have different colors, sort of a purple, a yellow, and a red. So we want to start thinking about bonding theories for coordination compounds. And are there any models or bonding theories that we can use to explain and predict the color of coordination compounds and maybe some of the other properties, such as magnetism? So in this lecture, we're going to be talking about bonding theories for coordination compounds. So we'll talk about some of the bonding theories that we've discussed back in Gen Chem 1 and which ones we can apply to coordination complexes. And then we'll be introducing a new bonding theory called crystal field theory. Okay, so I want you to pause this lecture really quickly and think about and write down what were some of the bonding theories and models that we used to describe molecules back in Gen Chem 1. Okay, so hopefully you thought of Lewis dot structures, VSEPR, valence bond theory or hybridization, and molecular orbital theory. So we used Lewis, VSEPR, and valence bond theory typically together to get information about the shape and then ultimately information like dipole moments. We also used a theory called molecular orbital theory because valence bond theory, VSEPR, and Lewis are limited, and molecular orbital theory was the most accurate bonding theory. But if you remember, molecular orbital theory was pretty cumbersome. So there were some issues with MO theory, and there's a reason why we don't use it as heavily as Lewis, VSEPR, and valence bond theory when we're making quick approximations. So just to remind you about valence bond theory, it was developed in 1930 by Linus Pauling, and it combined ideas of Lewis dot structures with the Schrödinger wave equation to describe bonding. Valence bond theory was used in conjunction with VSEPR to determine shape, and the orbitals that form when bonding occurs are different from the atomic orbitals in the isolated atoms. And these were called our hybrid orbitals. Hybrid orbitals, you have conservation of orbitals just like you have in molecular orbital theory, where your total number of hybrid orbitals is equal to the number of atomic orbitals that mix. So you have conservation of orbitals. The type of the hybrid orbital formed varies based on which orbitals are mixing. So you'll get different shapes based on what atomic orbitals are mixing to form those hybrid orbitals. And then the shape and the orientation of hybrid orbitals maximizes the overlap with the other atom in the bond. So you're maximizing the ability for these two atoms to share electrons. So this is just a quick example of beryllium chloride. If you draw the Lewis dot structure, BeCl2, it has this steric number of 2. So this is sp hybridization. So we have one s and one p orbital mixed together to form two sp hybrid orbitals. And this hybrid orbital has the correct shape to give this 180-degree angle, which we would predict from VSEPR based on this Lewis dot structure. And so if we were going to show what these mixing of orbitals looks like, a 2s orbital and a 2p orbital mixed together to form two sp orbitals. So we have one electron in each sp orbital, and then your 2p orbitals are empty. And then these sp orbitals are ready to overlap with orbitals on chlorine to form a bond. So that's what this looks like. We have our 3p orbital from chlorine overlapping with the sp orbital to form this sigma bond. And we also looked at more complicated atoms such as sulfur hexafluoride, SF6. So this has a steric number of 6. So you need 6 atomic orbitals to mix. Remember that your steric number tells you the number of atomic orbitals mixing to form hybrid orbitals. So for SF6, we would have our 3s orbital, 3 p orbitals, and then 2 d orbitals mix all together to get 6 sp3d2 orbitals. 1 electron in each one of those sp3d2 orbitals is going to overlap with the 2p orbital on fluorine. And again, you'll have 6 sigma bonds or single bonds. This will be an octahedral geometry. Okay, just as a quick reminder, when we talk about sigma orbitals, we're talking about end-to-end overlap. If you look down the bond axis for a sigma orbital, you see something that's spherically symmetric. If you look down the bond axis for a pi orbital, you see electron density above and below and a node along the bond axis. So end-to-end overlap are sigma orbitals, side to side are what we call pi orbitals. And if you have something like a double bond, you have 1 sigma and 1 pi bond. And if you have a triple bond, you have 1 sigma and 2 pi bonds. So this is just a reminder from Gen Chem 1. So here's ethylene gas. You have your sigma overlap that's taking place from your hybridized sp2 orbitals, and then you have your unhybridized 2p orbitals that can overlap side to side. So you have 1 sigma and 1 pi interaction to give this double bond. And here's acetylene, which has a triple bond. So again, you have your sigma overlap, and then you have 2 sets of unhybridized p orbitals for that pi interaction. Okay, so that's just a reminder of valence bond theory, but now we need to talk about valence bond theory specifically in coordination complexes. So remember that for coordination complexes, your ligands act as a Lewis base and your metal ion acts as your Lewis acid. And this is called a coordinate covalent bond. And in terms of valence bond theory, we say that the filled orbital of the ligand overlaps with an empty orbital of the metal ion. So we've got a filled orbital on our ligand overlapping with an empty orbital on our metal. So the valence bond model proposes that the geometry of the complex ion depends on the hybridization of the metal ion. So let's look at an example. Here's hexaamine chromium 3+. So this is an octahedral geometry. It's got a steric number of 6, which means that we need 6 orbitals mixing together to form the correct geometry. So if you've got chromium 3+, this has a D count of D3. So if we think about our empty orbitals are 2 orbitals from our 3D sublevel, and then our 4s and our 4p sublevel are empty. So these 6 orbitals are going to mix together to give a hybridization of sp3d2. So just like we already saw sp3d2 for SF6, we have a very similar hybridization taking place for our chromium 3+, but it's a little bit different because it's these upper level empty orbitals that are hybridizing together. They're empty orbitals. So then the lone pair from 6 different amine ligands can go ahead and donate to those empty hybridized orbitals so that we end up with 6 coordinate covalent bonds. Here's another example. This is tetrahydroxo zinc 2. So again, we have zinc 2+. This is D10. So zinc 2+ has a completely filled D sublevel. This is a steric number of 4. Your 4s and your 4p orbitals can hybridize together to form sp3 hybrid orbitals, and they're empty. So then the electrons from your 4 hydroxo ligands can donate into those empty orbitals to form these sigma interactions. So again, we have valence bond theory that can help us understand what this coordinate covalent bond looks like. Okay, but we have an issue with valence bond theory. So valence bond theory is really nice for helping us understand what these coordinate covalent bonds look like in terms of orbital overlap. But the big problem that we have is, remember I showed you that coordination complexes are colorful? Well, valence bond theory does not predict color or magnetism for these coordination complexes. So we need another theory. We talked about molecular orbital theory back in Gen Chem 1. Molecular orbital theory is basically the gold standard. It was developed in 1933 by Hund, Mulliken, Slater, and Jones, and it's based on quantum mechanics. So valence bond theory is based on localized overlap of atomic orbitals, whereas molecular orbital theory is based on the actual wave functions. So it's a molecule is pictured as a collection of nuclei with electrons delocalized over the entire molecule, so the actual wave functions. So molecular orbital theory is mixing of atomic orbitals to form delocalized molecular orbitals, or mixing of atomic wave functions to form these delocalized molecular wave functions. Remember, in molecular orbital theory, orbitals mix if they have similar energy and shape. So we talked about if we have two s orbitals mixing, they can form both constructive and deconstructive interference, or bonding and anti-bonding orbitals. And we also have this conservation of orbitals. Number of atomic orbitals equals our number of molecular orbitals. And we can draw these molecular orbital diagrams. So here is it's a partial representation of the molecular orbital diagram for hydrofluoric acid. You have your bonding interaction and your anti-bonding interaction, and this is our sigma bond. Valence bond theory is really good for predicting shape, but cannot predict bond order, stability, or paramagnetism. And molecular orbital theory does not give us very much information about shape, but it does tell us about paramagnetism, bond order, stability, and information also about dipole moment and distribution of electron density. So molecular orbital theory is more accurate, but it's also more difficult to visualize. In Gen Chem 1, we often used these theories together to help give us an overall picture of the molecule. But we have an issue with molecular orbital theory when it comes to coordination compounds. So if you remember back to Gen Chem 1, we didn't do molecular orbital theory for anything more complicated than diatomic molecules. And that's because molecular orbital theory gets very complicated very quickly. You're using Spartan to do computations. You're doing calculations of the wave functions of these coordination complexes. So it takes quite a bit of calculation power to get information of these complex ions based on molecular orbital theory. For coordination complexes, we can use valence bond theory to visualize the shape, but we need another theory to help us predict properties such as stability, paramagnetism, and spectroscopy. Here's two different vanadium complexes: hexa-aqua vanadium 2+, hexa-aqua vanadium 3+. The +2 oxidation state is purple, the +3 oxidation state is yellow. Or this hexaamine chromium 3, or pentaamine chlorochromium 2. Chromium 3. So this has, all that's changed here is just one of the ligands has changed. And so small changes result in these color changes. So change in oxidation state can cause a change of color. Substitution of a ligand can cause a change of color. And so we want to understand why that is. So we need a new theory, partially because molecular orbital theory is really great, but it's challenging when we're dealing with these really big molecules. Crystal field theory is a new theory that we're going to be talking about, or a new model, or new to you, I should say, because it was developed in the 1930s. But it is a model that we can use to make approximations about complex coordination complexes. Crystal field theory is based on the idea that the metal-ligand bond is purely electrostatic. Now, that's not actually true, but if we make this approximation, we can make some predictions about the properties of these different coordination compounds. So it's based on the idea that the metal ligand bond is purely electrostatic. So we're using Coulomb's law, that potential energy is proportional to the product of the charges divided by the distance between those charges. We need to consider the shape of the 3D orbitals also, because we're saying that this metal ligand bond is electrostatic. So we know that we have electrons on our ligand, and we know that there are electrons on the metal that exist specifically in these d orbitals. So we need to understand the shape of our 3D orbitals, because our d orbitals that are pointing directly at our ligands are going to have some electron-electron repulsion. So when we're thinking about potential energy, our d orbitals that are pointing directly at our ligands will be higher in energy because of Coulomb's law. They'll have this electron-electron repulsion. And then our d orbitals that are pointing away from the ligands will be lower in energy because they don't experience the same electron-electron repulsion. So in the next lecture, we'll go through a lot more detail on crystal field theory.